Hello students, we are looking at trying to solve a linear programming problem by graphing, and the problem that we're looking at is to minimize z equals 5x plus 3y subject to the inequalities 4y plus 5x is greater than or equal to 32, 3y plus 2x is greater than or equal to 16, y plus x is greater than or equal to 7, x is greater than 0, and then y is greater than 0. So those last two standard constraints, y is greater than 0, x is greater than 0, means that we're dealing here in the first quadrant. And we want to start by graphing each of those three equations. The 4x plus, or minus, or 4y plus 5x equals 32. And one of the nice ways to do that is to look at the intercepts. Say what happens if, say, y is equal to 0. If y equals 0, then our equation essentially just becomes that 5x equals 32. So x would be 32 divided by 5, which is 6.4. So on the x-axis here, I'm going to have an intercept about 6.4, which would be right about in that location. And for that same line, if x is 0, if x is 0, we're looking at the equation 4y equals 32, so y equals 8, so the y-intercept would be the point 0, 8. So I'm going to cross the y-axis here at 8, which is right about that spot. And so then I want to draw a line connecting those two as best I can there. All right. And then it's kind of nice to look at what side of that line is our solution region. If you try the test point 0, 0 in the original equation, you'll have 0 plus 0 is greater than or equal to 32. That is a false statement. And so I don't want the side of the equation with the origin on it. I want the side that's opposite that. So I'm going to put some little tiny marks out here to indicate that I'm looking at my solution region being that area above and to the right of that line there. All right, and then the next equation is 3y plus 2x equals 16. I'm going to do the same sort of thing. If x is 0, the equation drops to 16. 3y equals 16, so y would equal 16 thirds, which is just a little bit more than 5. It's 5 1/3. So it's going to be somewhere in that area. So one of the intercepts is 0, 16 over 3. The other intercept would be if you put y to 0, and if y is equal to 0, I'll have the equation 2x equals 16. So dividing both sides by 2 gives us x is equal to 8. So 8 is here. And so this line would come down across like that. And again, I'm still looking at what side of that needs to be shaded. And 0, 0 is not a solution. Again, 0 is not greater than 16. So I want the side that's opposite that. So don't include the 0, 0 side. I want the side that's out here. All right. And then finally, I've got x plus y equals 7. If x is 0, x is 0, y is going to be 7. So that would be at this point. And if y is 0, x is 7. So it looks like I've got a line that kind of comes through here. I wonder, I'm going to have to look a little bit closer at that intersection point. I'm not sure all three lines intersect in the same point. It would be nice if they did, but I don't think that's exactly the case. Let's actually look at that. Let's look at, well, still 0, 0 is not a solution to that one either. So my feasible region will be the area that's out here. Everything out here is going to be my feasible region. Okay, but I do need to check what's happening here in that center area. It's a little confusing in there. If I'd have drawn it really nicely, maybe I could get it to be a little clearer in there. But somewhere in there I need to do some checking. Let's see where they're corner points. So I've got, if I look at where does the 4y plus 5x equals 32, where does that intersect y plus x equals 7? Let's take and let's multiply the bottom equation by -4. So that will give us let me kind of scroll down here. I've got can't remember it now. 4y plus 5x equals 32, and minus 4y minus 4x is equal to 7 times -4, -28. If we add those two equations together, we get x equals 4. And if x is equal to 4 and x plus y equals 7, then y equals 3. So it looks like one of these points in here is at 4, 3. And I don't suppose that that's the intersection point. That's where the top and the bottom equation are going to intersect at 4, 3. I don't suppose that's where, let's look at 3y plus 2x equals 16. Is that 3 times 3 plus 2 times 4 is 9 plus 8, that's 17. Okay, so that's not on the intersection point. So it looks like I do have 3 different intersection points in there. I've got, I'm going to have to look a little closer at that. One of those intersection points is this 4, 3. And if I look at where does 3y plus 2x equals 16 intersect x plus y equals 7, I'm gonna do the same sort of thing. Let's multiply the bottom equation by -2. -2. That way, when I add them together, the x's will cancel out. So 3y plus 2x equals 16, minus 2y minus 2x equals -14, and we add and we get y is equal to 2. And so it looks like I should have another intersection point. So if x plus y is equal to 7 and y equals 2, then x would have to be 5. So 5, 2 is another intersection point. And then the third thing I need to look at is where does the two kind of hard ones, where does 4y plus 5x equal 32 intersect 3y plus 2x equals 16. And let's see, how can we get those to cancel? Well, if I take the top equation and multiply it by -3 and the bottom equation by -4, that'll give me -12y minus 15x equals -96, and -12y, whoops, I wanted these both to be, one of these to be positive, plus 8x equals 4 times 16 is, check my calculator here, 64. And actually, let's make that last one all positive. Let's multiply through by -1. Multiply by +4, not -4 up there. And then it'll be positive. So now I add, the y's cancel. I'll get a -3x when I add the two x terms together. No, -7x. Let's add correctly. So, yeah, -15 and 8 gives you -7. And -96 plus 64 is going to give us -32. And so dividing by -7, x is equal to 32 divided by 7, 4.57, and some change there. So if x is 4.57, or if preferred 32 over 7 is more exact, let's go up and see where that, what would y be. Let's take this equation. Let's take the 3y plus 2x equals 16, and we'll plug in the 32 over 7 in there. 3y plus 2 times 32 over 7 equals 16, so 3y plus 64 over 7 equals 16. If I subtract 64 over 7 from both sides, I'll get 3y equals 16 minus 64 divided by 7 is about 6 point something, 6.85. And then divide that by 3, and I get 2.28. Alright, so I need to kind of look at what's the relationship between those 3 points. Between 5, 2, would be right about there. 4, 3 was the other one. 1, 2, 3, 4, 1, 2, 3. 4, 3 would be in that spot. And then the other one I have is 4.5 and 2.7. So what I've got is, it looks like these lines are intersecting. That should be at 2. That should be a little bit higher. So intersecting, making kind of a little triangle in there. Kind of clear that up here a little bit. So there, and I've got another point. It looks like it's just below that. So it looks like that's kind of a good thing, that the 2 outer points are the ones that are nice points. It's the point 4, 3 and 5, 2. So that should tell us what all our corner points is. Going back up to our graph, I've got corner points. I've got this upper corner point up here at 0, 8. I've got a corner point down here at the bottom at, looks like 8, 0. And then I've got 2 other corner points. There are 2 corner points hiding in here. One at 5, 2, and the other at 4, 3. So what we'd want to do is we'd want to check these 4 points in our z equation, our objective function that we're trying to maximize, and see which of those makes things the smallest, because we're trying to minimize again. So let me kind of clear out some space here, do a little erasing. If x is 0 and y is 8, then z would equal 5 times 0 plus 3 times 8. That's going to give me 24. At 8, 0, z would equal 5 times 8 plus 3 times 0, which is 40. And at 5, 2, z would equal 5 times 5 plus 3 times 2. 25 plus 6 gives us 31. And 5 times 4 plus 3 times 3 gives us 29. So it looks like my smallest value here is 24 at 0, 8. So the solution would be, our minimum value is 24, z equals 24, at x equals 0, y equals 8.